Fourier transform of impulse, that is delta t. What is the Fourier transform of delta t?
1.
It is 1. It is easy to verify. E to the power minus t delta t to the power minus j omega t dt. This is integral minus infinity to infinity. What? Delta t dt, that is 1. Because delta t is non-zero only at t equals to 0. So this is 1. That this is not in the normal sense. This is in the generalized sense. Okay. This Fourier transform pair delta t 1. This is in the generalized sense. That means if you take the inverse Fourier transform of 1, what is inverse Fourier transform of 1? This is the inverse Fourier integral 1 into e to the power j omega t d omega. That is not equal to delta omega, but in some generalized sense. Anyway, I will explain that that what is meant by this generalized sense. Similarly, this is a delta function. This is a delta function in the time domain, and in the frequency domain, if you consider a delta function, let's say we consider delta omega. X of j omega is equal to delta omega. Okay, so the inverse Fourier transform we can find. Inverse Fourier transform is 1 upon 2 pi minus infinity to infinity delta omega e to the power. What is that integral?
1 upon 2 pi.
It is 1 upon 2 pi. So this is another Fourier transform pair. So 1 upon 2 pi we can cross multiply and we will get this result. It is 1 2 pi delta omega, this Fourier transform pair, and if a delta function in the time domain, it is 1. Okay, these two are very important results. Both these are in the generalized sense. Okay, now if you consider a shifted delta function, instead of delta omega, I am considering an impulse at, let's say, omega naught. Okay, so this is 1. So x of we can write that x of j omega is delta omega minus omega naught. What is the inverse Fourier transform of this? Inverse Fourier integral is 1 upon 2 pi. What is this integral? Sorry, it is d omega. What is that?
Sir, 1 upon 2 pi e raised to power
It
j
is
omega
1
naught
upon
t.
2 pi e to the power j omega naught t. Okay, that also you can easily verify using the property of impulse function, because this function is non-zero only when omega is equal to omega naught. So you'll directly get this result. So that is another standard result. If you cross multiply this, you can get this term. It is e to the power j omega naught t. Its Fourier transform is 2 pi delta omega minus omega naught. Here, e to the power j omega naught t. Its Fourier transform is 2 pi delta omega minus omega naught. And by using this Fourier transform pair, we can find a Fourier transform of periodic signal. Okay, periodic signal. So far we have defined Fourier transform for a periodic signal. We can use this result to find the Fourier transform of periodic signals. And why do we need Fourier transform of periodic signals? We already know the Fourier series representation of, for a periodic signal, it is Fourier transform, and for periodic signal, it is Fourier series, isn't it? That is what we have discussed so far. But in many cases, it is convenient to have a unified Fourier representation for both the both periodic and aperiodic signals. That's why we are going for Fourier transform of periodic signals. If we consider a periodic signal xt, let's say its Fourier series coefficients with respect to period t naught is ak, then we can write this signal xt as linear combination of this one, harmonically related complex exponential signals, right? Now, if you consider this expression, this is by using the Fourier series summation, you get this this expression for the periodic signal xt. Now, if you use this, what is the Fourier transform of this? Okay, again here we assume the linearity property. Linearity, the Fourier transform is the satisfies the linearity property. That means if x1t linearity property states that if x1t Fourier transform is x1 j omega, x2t, x2 j omega, and if we consider linear combination of x1t and x2t, a1 x1t plus a2 x2t, then it is a1 x1 j omega plus a2 x2 j omega. That is the linearity property of Fourier transform. That proof is straightforward. I am not going to derive that. So if we apply this linearity property here, tell me what are the Fourier series, what is the Fourier transform of this? This is a constant. Then what about the Fourier transform of e to the power j k omega naught t? Using this
Omega
result,
minus k omega naught.
it is delta omega minus k omega naught, isn't it? It is an impulse in the frequency domain. It is not a impulse. It is a sequence of impulses at integer multiples of omega naught. And the strength of those impulses are, is it ak?
2 pi.
Yeah, it is 2 pi ak. It is 2 pi into ak. So this is the Fourier transform of that periodic signal. Okay, it is a Fourier transform of the periodic signal. Let us consider one example. Let's say xt is equal to cos 2 pi t. What is the Fourier transform of that signal? What are the Fourier series coefficients? How many non-zero Fourier series coefficients? A1 is 1 by 2. And which is the other non-zero coefficient?
A minus 1.
A1 and A minus 1 are 1 by 2. So what is the Fourier transform of that? Here, there are only, in the summation, there are only two non-zero terms that corresponds to 1, k equals 1 and k equals minus 1. So is it 2 pi into A1 is 1 by 2 delta, when k is 1, it is omega. What is omega naught here? Omega naught?
1.
Omega naught is 1.
2 pi.
Omega naught is 2 pi, isn't it? Period is 1, T naught is 1. So it is period, this omega naught is 2 pi. And then plus what? 2 pi into, when k is minus 1, again it is 1 by 2 delta omega plus k omega naught. So this is the Fourier transform of the signal cos 2 pi t. Now what is the spectrum of the signal? Is it a real valued spectrum or complex valued spectrum in this particular case?
Real value.
It is real valued. So we can directly sketch that x of j omega. What is the shape of that? X of j omega.
Impulse are 2
There
pi
are-
and minus 2 pi.
There are two impulses, one at 2 pi and the other one at minus 2 pi. And what are the strengths of those impulses? What is the strength of this? It is pi and both are having strength pi, isn't it? So this is a spectrum of cos 2 pi t. This is a spectrum of cos 2 pi t. There are two impulses at 2 pi and minus 2 pi. Okay. Now what about this signal cos pi t? Can you tell me what is the spectrum of this signal? Cos pi t? Is it the same spectrum?
Compressed.
Sorry?
Sir, the impulses would be at minus pi and pi.
The impulses will be at minus pi and pi, because if you find the Fourier series of this, what is the fundamental period of this? Cos pi t? T naught is 1. With respect to that period, A1 and A minus 1 are 1 by 2 with respect to its fundamental period. And then we can, sorry,
T naught will be 2.
T naught will be, oh sorry, T naught will
2.
be 2. Yeah, so T naught is 2 and omega naught is pi, isn't it? T naught is 2 and omega naught is pi. So then you can use this expression. You will get two impulses, one at pi and the other one at minus pi, and the strength is same pi, isn't it? This is the spectrum of cos pi t. And here you can see that even though the Fourier series are the Fourier series coefficients same in both the cases? A1 and A minus 1 are 1 by 2 in both the cases, right? But we cannot say that the Fourier series coefficients are same, because we are considering this Fourier series with respect to different periods, isn't it? Is it?
Yes, sir.
In this case, we are considering with respect to period 1, and here we are considering with respect to period 2. So even though the numerical value of the coefficients are same, but their spectrum is unique. Here there are two impulses, one at minus pi and pi, other one at pi. So here minus 2 pi and 2 pi. So even though the numerical value of the Fourier series coefficients are same, their spectrum is different. Okay.
Yes, sir.
So that is about Fourier transform of periodic signals. Now tell me what about sin pi t? What is the spectrum? Sin pi t. Tell me the expression.
So pi into delta omega naught minus pi minus pi times delta omega naught plus pi.
No. Something is missing here.
Divided by J.
J.
Divided by j. Is it?
Yes.
Now tell me what is the spectrum of this signal?
Complex value.
Complex value. So we have to plot what? Magnitude and
Magnitude.
phase separately. What is the magnitude spectrum? Magnitude spectrum?
Impulse at minus pi and pi.
Impulse at minus pi and pi. What is the strength of that impulse?
Pi.
Is it this? Now what about the phase spectrum? What is the value of the phase at pi when omega is pi? This term, isn't it? When omega is
Minus
pi,
pi
this
by
term
2.
is non-zero. Then it is what?
Minus pi by 2.
It is minus pi by 2, because phase angle of j is pi by 2. Since this is in the denominator, it is minus pi by 2. And what about the phase at omega equals to pi? Sorry, minus pi?
Pi by 2.
It is pi by 2. It is pi by 2. Because this is minus, and because of this minus sign, it is pi by 2, is it? It is pi by 2. So this is the phase spectrum. Okay.
Sir?
Hmm.
So isn't it be reversed, like at pi it's pi by 2 and at minus pi it's minus pi by 2?
No, where is this? Which one is this one? Omega naught minus pi means. Oh, sorry, it is omega naught, not omega naught minus pi. Omega minus pi, isn't it? Omega minus pi and omega plus pi. Is it?
Yes, sir.
So where is this point?
Sir, it will be 0 and the phase will be determined by omega plus pi term.
No, this point is where? This is non-zero when? When is this non-zero? When omega is equal to?
Minus pi.
Is it minus pi? When omega minus pi is 0. Omega minus pi 0 means what? When omega is equal to pi, is it?
Yes, sir.
So is it this point?
Okay,
The phase
sir.
angle is minus pi by 2.
Okay, sir, I will get it.
This because this is don't think that this is the negative side and this is the positive side. This is non-zero when omega is equal to pi. So this point. Okay.
Okay, sir.
If you consider an impulse train in the time domain, let's say 0 t naught, it is a periodic signal and strength 1. If you consider an impulse train in the time domain, it is a periodic signal. So the expression for that signal is xt is isn't it? That is the expression for that impulse train. What are the Fourier series coefficients? Fourier series with respect to its fundamental period t naught. What are the Fourier series coefficients of an impulse train?
By T naught.
Sorry?
1 by T naught for all.
1 by t naught for ak is 1 by t naught for all k. Those are the Fourier series coefficients. Now we know this relation. If xt is having Fourier series coefficients ak, then its Fourier transform x of j omega, that is 2 pi ak delta omega minus k omega naught. Okay. Now if we substitute this value here, we will get this minus infinity to infinity. 2 pi ak is 1 by t naught. So 2 pi by t naught delta omega minus, what is omega naught here? Is it this? What is the shape of this? In the time domain, it is an impulse train. What about the shape in the frequency domain?
Impulse train.
It is another impulse train, isn't it? So its spectrum is okay, 0. And which point is this? This is function of omega. And this is 2 pi by t naught. And this is 2 into 2 pi by t naught, like that. And this is minus 2 pi by t naught. And what is the strength? 2 pi by t naught. Is it? This is a spectrum of that impulse train. So here you can see that in the time domain, it is an impulse train. In the frequency domain or in the Fourier domain also, it is an impulse train. Only difference is that their strength is different and these points are also different. What will happen if we increase the value of t naught? If we increase the value of t naught, what will happen? This separation increases in the time domain. What happens here in the frequency domain?
Separation decreases.
So you can see that if we expand in the time domain, there is a compression in the frequency domain, time compression. And we observe this property for rectangular pulse also, isn't it? We have seen that for a rectangular pulse, minus t1, its Fourier transform is a sinc function. Okay. And these points are pi by t1 and minus pi by t1. So same thing there also. If we compress the signal, that means if you reduce the value of t1, this expands in the other domain. And if we expand the signal in the time domain, its effect in the frequency Fourier domain is compression.